Hello everybody and welcome to another edition of NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 38 and we will go forward from where we left in the previous lecture, primarily looking into the subthreshold swing and transconductance. Just to recapitulate what we did in our previous turn so that you are aware of for this turn. One is we looked into the subthreshold swing, on what factors it did depend, how can we improve it, and we also finally ended up looking at the subthreshold swing for an N channel MOSFET, and we saw that at lower temperature the subthreshold swing is very small, and as you increase the temperature for a fixed current the subthreshold swing goes on increasing. We also saw that at lower value of drain to source current the subthreshold swing is small for any temperature, and as you increase the drain current the subthreshold swing increases drastically. With this background, let us come to today's lecture. Now we will be looking into P type MOSFET, right. So basically here the your charge carriers are primarily here, majority are basically holes here, right. And so you will have P type or holes available here, and this is a P type semiconductor I am assuming in for all practical purposes. So if you look at the left hand side graph here, it shows the variation of ID as the drain to source current with respect to gate to source voltage, right. And these are basically experimental data taken from bulk P MOSFET, and the channels are generally long because it is approximately 0.5 micron channel has been taken. And as you can see, just like in NMOS, as the obviously the slope actually starts to reduce as you move from low temperature to high temperature, meaning the subthreshold behavior is also the same. If we look at the subthreshold swing versus current, interestingly there is a general trend that for lower temperature the subthreshold value is smaller, and as you go on increasing the value of your temperature it goes on increasing, but it is not as clear cut as a N type MOSFET. So you can see there are a large amount of crossovers and so on and so forth, but practically speaking we can assume that for a fixed value of EOT and aspect ratio of 1.2 to 0.5 micron and a fixed value of VDS which is minus 0.1 volts. So basically I am actually less than saturation, below saturation, and I can see that the subthreshold swing goes on increasing as I move from a lower temperature to a higher temperature. Exactly the same sort of observation as NMOS. So observation wise they are exactly the same. The only thing which you should note is that the value of SS even at 10 Kelvin is 2 times at least larger than compared to NMOS, which means that P MOSFET will behave slowly as compared to NMOS, at least at lower temperature, because holes have their effective mass of holes are relatively much larger. Effective mass is larger for holes, right, and therefore your M star starts to becomes larger, and therefore your mu goes on reducing, and therefore it becomes difficult for the device to switch on. So that is the reason you see that about 2 times increase in the subthreshold swing at even at lower temperature when you assume 10 Kelvin as the lower temperature. So we have finished with subthreshold slope concept with respect to the device. Let us see how the substrate doping affects the subthreshold. Substrate doping is the doping which you do on the substrate side and you try to find out the effect of the subthreshold swing. Now we know that CD, the depletion capacitance, is inversely proportional to WD. So as the substrate doping increases, the depletion width decreases and the CD increases, which means that as Na goes on larger, WD decreases and therefore CD increases, right. When CD increases, you know your SS increases and becomes worse, right. So basically if you basically increase the substrate doping and you see therefore with CD increases, as CD increases we have already seen that there will be inversely dependency on the value of the subthreshold swing. Let us look at the right hand side figure here, which plots subthreshold slope with the variation in temperature for various amount of substrate doping which you see here. As you can see very rightly, for a fixed temperature, take any temperature, let us take 150, right, and plot a line across 150 and you see that higher substrate doping will give you a much larger subthreshold swing as compared to a lower one, right, and that comes from this left hand side explanation in a sense, right. it becomes from there, it comes out to be like that. The another observation is post around 25 to 50, let's take 50 around. If you go on increasing the temperature, there is almost a linear increase in the value of the subthreshold swing, which means that for a fixed value of Na, if your temperature goes on raising beyond 50, there will be a constant rise or a linear rise in the value of your subthreshold swing. That is, a linear increase will be there. However, below around 30 Kelvin, so there is basically a dip around 10 to 30 Kelvin, right. This dip which you can see here, it will be visible more to you at much lower substrate doping concentration somewhere here, let us suppose. So, let us take this one. So, if you plot a graph here, it is around 20 Kelvin or so. At 20 Kelvin or so, when your substrate doping concentration is 3.7 into 10 to the power 15, you end up having minimum value of subthreshold swing. So, if you start from absolute 0, as you increase the temperature, the subthreshold swing starts to decrease, right, reaches to a bare minimum or to the minimum value, sort of a minima, and then shoots up linearly as you increase the temperature, right. And this comes as sort of a boon in disguise to all of us who are working in cryo, that I can therefore operate at a lower temperature and still get a relatively low subthreshold swing. The reason why the subthreshold swing reduces as you increase the temperature from 0. So, first let us look step by step. As you increase the temperature from 50 Kelvin above, the subthreshold swing goes on increasing, which is but obvious. We have already discussed this point earlier. But what happens at extremely deep cryo is, as you make the temperature go higher and higher, why the subthreshold swing goes on reducing at lower temperature. So, basically as the temperature increases, subthreshold swing reduces, means it is easier to switch, right. So, let us take two issues, one is 30, let us take, and 20 to 30 Kelvin, and above it SS increases and below it SS increases, right. So, there is a minima here. So, why does the SS increase as you reduce the temperature below it? Because the localization of states at lower temperature. At extremely low temperature, it is very difficult for traps to release the charge carriers, and therefore, even if you go on doing anything else, it becomes very difficult, and therefore, since they do not participate, the subthreshold slope actually becomes larger and larger at lower values of temperature, right, because of this. Now, again the same graph as I discussed with you, again we take in this case as SS to be equals to KT by Q, natural log 10 1 plus CD plus CIT upon C oxide, where CIT is basically the interface trap charges, which means that the subthreshold swing is directly proportional to 1 plus CD plus CIT by C ox, right. I can add here actually CD plus CIT plus C ox here as well, and that increases then in NA value, and these are all measured values which you take for various values of temperature, the substrate doping variation on SS, right, and that is the reason we need to be very careful as far as finding the value of SS near the absolute 0 and very near to around 20 to 30 Kelvin. Now, let us switch gears and let us start with a new topic within the whole gambit of device parameters, and that is transconductance. We have already told you what is transconductance. It is basically the rate of change of drain to source current with gate to source voltage, and let us go one by one and see how it works out. Let us look at the right hand side figure first, and if you plot ID versus VGS, interestingly, let us look at the linear scale that is visible very easily, that initially the current is almost constant independent of the value of temperature. For any temperature, the current is almost constant when your gate to source voltage is below 0.3 volts, right. When your gate voltage is below 0.3 volts, the current is almost constant independent of the temperature, right. Suddenly, as you move ahead and go past the threshold and you move ahead, your current starts to increase, and that is expected also, and of course, lower the temperature, higher is the current, for reasons again obvious by this time around. However, interesting thing which you should note is, and that is more important, is that the rate of increase of current with gate voltage for a lower temperature is much higher, implying that the transconductance is much higher for a lower temperature, right. So, if you are operating a device at 4.2 or 4.3 Kelvin, then it is much more, it's much more higher transconductance which it gives, right. it gives you much higher transconductance as such. And therefore, if you understood this right hand side curve, which is a very standard one, please note the fact that for lower temperature, beyond a particular VGS, the current actually starts to fall. So, you would expect to see a GM reduction taking place at higher values, and this reduction takes place much earlier for lower values of temperature. So, let us just take this as a benchmark graph and try to replicate it in the transconductance graph. So, on the left hand side I have a transconductance versus gate voltage, gate to source voltage. As you can see, at very low values of VGS here, which is corresponding to here, since the current is not changing, your del ID is almost 0, del ID del VGS will be almost 0, and your GM is almost 0 here, right. Suddenly beyond 0.3 you see a sudden rise in the value of GM. Not only that, a 4.3 Kelvin change is much larger as compared to even a 77 Kelvin change. As you go to 300 Kelvin, it is almost flattened out. So, and beyond a particular point, 0.3, 0.32 to 0.3334, the value of GM for the 44.3 Kelvin falls drastically down, and it becomes so low that very large values of VG, it almost becomes lower than even 300 Kelvin. So, the sweet spot for GM to be maximum is somewhere around 0.3 to 0.4 or 0.5, where the transconductance is maximum. If you operate your device beyond that, rather than gaining in low temperature and cryogenics, you will be actually losing, because the transconductance has fallen down to such a low value that the overall gain will be relatively small. So, let us divide this whole graph into 3 parts, part number 1, 2 and 3. 1 is where you have low GM or 0 GM, 2 is the part where the GM is increasing function of VGS, and part 3 is where the GM is a decreasing function of gate to source voltage. Now, let us go one by one. Now, so let us look at the transconductance at cryogenic temperature, which is typically below 77 Kelvin, which means we will be looking into the red graph and this black graph here. And here the carrier mobility tends to increase, because we have already discussed this point. Because of reduced phonon scattering, the carrier mobility tends to increase, which tends to make your rate of change of current higher, and therefore GM higher. Further, there might be also, there is actually a threshold voltage shift due to dopant freeze out, right, and therefore there is a dopant freeze out, there is a change in the Fermi level, and which results also in that. However, please keep in mind that the interface trap density and the subthreshold slope, they obviously behave in a different fashion. Now, let us look at the impact of transconductance on the transconductance by these variations. For long channel devices, primarily there is an improved mobility which happens, right, and that increases the value of transconductance. For very short channel devices, the main reason is basically velocity saturation and quantum confinement. Velocity saturation means that the velocity of the charge carriers cannot go beyond a particular point, because the scattering mechanisms becomes as fast as your drift velocity. Further, when there is a quantum confinement, there is the charge particles are confined to certain energy levels, right, and this may limit the gain in the transconductance, and that is the reason you see your transconductance goes up to 250 microsiemens approximately, and then starts to shoot down, because at those values quantum confinement effect takes over, and this tend to make the rate of change of current fall, which means that the behavior actually becomes a device and temperature dependent, which is quite critical for working at the cryogenic temperature. Right? Device, why? Because the parameters are chosen in such a manner that they are like that. Now, why do we study transconductance and cryogenic? I have given you a brief insight. Quickly let us go through the various application domains where you require to get this transconductance. Typically in quantum computing, when you do a readout or control of the qubits, you require high GM in order to ensure very fast analog circuits. Or transconductance is higher, basically meaning it is very sensitive, your gains are very high, and even at low power you will be able to extract the information out of the readout signal. Similarly, you need to design a low noise amplifier design, where you require the gain to noise ratio or signal to noise ratios to be relatively high. This can only happen when you have a larger transconductance. The third areas are radiation hardened space electronics, where the temperature is very small. And finally, we look into the 2D materials and SOI devices, where there is a band trailing, trap behavior, carrier freeze out taking place at cryo temperatures. So, if you want therefore that all these devices, emerging devices or more devices to work at cryo, the implication of transconductance should be known to you as a designer. So, As I discussed with you, there are 3 regions, 1, 2 and 3. Region 1 is point where the GM is, in fact GM decreases with temperature, right. So, I do not know you can see it or not. If you look at region 1, which is this one, typically with temperature, if you see, there is actually, as the temperature increases, there is no fixed definition of how a GM behaves. So, you see at very low threshold below 3, even at 4.3 Kelvin, you see it is almost 0 GM. It is almost a straight line. The black line is almost a straight line parallel to VGS, but sticking to 0. Primarily meaning there are no charge carriers at subthreshold region at 4.3 Kelvin to contribute. Change in current is 0 and therefore you get 0. However, as you start increasing the temperature because of some electron hole pair generation, some current even at subthreshold, diffusion generated currents are there, which results in some amount of charge. Very small amount of current is available. So, GM actually decreases as temperature decreases in case of a region 1. In region 2, it is the reverse. As the value of your temperature goes on reducing, the GM goes on increasing, right, and it is just the reverse which is happening. Whereas in region 3, the GM shows a decline as VGS increases for all the values, be it 4.2 or 300 Kelvin, but the decrement in the 4.2 Kelvin is much larger as compared to 300 Kelvin or 200 Kelvin. So, the loss is much larger in region 3 as compared to region 1, right. Let us come to region 1 here, and in this region GM decreases with temperature, right, because the mobility increases at low temperature and the threshold voltage increases at low temperature due to dopant freeze out. So, the threshold voltage decreases, obviously your current actually starts to fall down. That is written in the third point of the bullet, right, and when the current decreases, there is a reduction in the transconductance. Now, 2 things happens, that the mobility improvement takes place, threshold voltage goes down. These 2 are opposing phenomena when we discuss about transconductance or current, right. So, what happens is the rise in the threshold voltage actually outweighs the mobility improvement, right, and that is the reason that the temperature variation of threshold voltage dominates, and therefore resulting in a reduction in transconductance in this region. So, at region 1, where your VGS is very small, almost in the subthreshold region of operation, almost near cutoff, the variation of threshold voltage takes over as compared to the increase in the value of mobility, right, and that results in such type of behavior in terms of transconductance. Let us look at transconductance in region 2. Region 2 is the one where you see a reverse swing. In this, GM increases with decreasing temperature. So, as the temperature goes on decreasing, the transconductance increases. Here the reverse takes place, the mobility enhancement takes over the threshold voltage increase, and therefore rate of change of current becomes higher at lower temperature. Moreover, if you look very interestingly, if you look at the maximum GM point, that increases with temperature reduction, right. So, if you look very carefully here, this is the point where you get the maximum transconductance, and however, as the temperature goes on becoming low, this shifts to the lower value of VGS, right. This goes to the lower value of VGS, the peak GM value. So, if you want to operate your GM for the most large amount of transconductance, for lower temperature the value of VGS is slightly higher, and as you reduce the temperature it goes down, as goes down, the peak shifts to go down. Now, region 2 is therefore the most favorable sort of region in cryogenic electronics, because it supports a very high transconductance region, and therefore your overall gain will be relatively high in this case, right, and that makes the region 2 most suitable for all practical purposes. Let us come to region 3. Region 3 is where your transconductance starts to go down for increased value of VGS, right. This is where the mobility degradation due to scattering takes place, and this is primarily because of surface roughness. Why? Because at higher value of VGS, you are pulling the charge carriers very close to the silicon dioxide interface, and therefore the number of scattering event increases, surface roughness based scattering event, and the mobility falls down, and therefore the drop is there. However, you need to look that the rate of fall for a lower temperature is much larger as compared to that of the higher temperature. So, higher temperature the degradation is not that heavy, and therefore for all non-cryogenic based design which we have been studying for last so many years in our BTech undergraduate and so on and so forth, we know that the fall is not a major issue for T equals to 300 Kelvin. But one thing as a cryogenic engineer or a very low temperature electronic engineer you need to understand is that at extremely low temperatures, the fall will be relatively very large, right. This large fall which you see at higher VGS is again, it is again to do with the rate of change rather than the absolute value of current. So, the rate of change of current is much higher that the transconductance reduces, right, because the number of charge carriers are anyway very less in case of very low temperature, and therefore, even a small change in the number of carriers or the carriers which are participating in scattering increases, the transconductance value goes down. Now, for T less than 77 K, which is the black and the red curve, high VGS and GM can become negative, indicating instability or inversion layer carrier freeze out effects, right. The GM can also become negative at very high VGS value. Negative effectively means that you would actually see reduction in the current, drain current, with increase in the gate voltage, right, and this is why there is a carrier freeze out which is happening at inversion layer. Now, the maximum value of GM is observed around 4.2 Kelvin, and therefore, extreme effect of mobility degradation is not seen here in this particular case. So, with this basic idea, let me recapitulate what we did in this lecture. We looked into primarily we started with subthreshold for a PMOS and explained to you what the PMOS subthreshold does. Then we went to transconductance. Within transconductance, we looked into region 1, 2 and 3, and we saw that region 2 at low temperature at cryogenics is the best operation, right, is the best mode of operation, and in region 3 you will have GM decrement, and even GM can go to negative value at high VGS because of carrier freeze out in the inversion region. So, we learned two things. Takeaway is that if you want to work at 4.2 Kelvin, the best operating condition in terms of input gate voltage is around 0.2 to 0.3, assuming that is where your threshold of the device is all about, right. So, I hope you enjoyed this lecture. Till we meet next time, goodbye.